Welcome, everybody. It was quite interesting to hear from the perspective of developers and general contractors and construction managers. I'm going to take us down the path of more of the mechanical and electrical. We traditionally represent about 20-25% of large projects. So Black & Macdonald, we're a electrical and mechanical contractor. And we've drank the Kool-Aid on 3D virtual modeling and using technology. So we view that there's 5 steps to having a successful construction project. Having accurate as-builts, doing a 3D design using the accurate as-builts, then using the model, do your purchasing. From your purchasing, the next is implement your quality control systems for your project. And then your productivity control, because we're driven by the bottom line. We have to be productive, efficient, and effective. So having an accurate as-built is the foundation, the first step in the planning process. And again, what we're doing is in construction, it's planning, planning, and planning. It allows us to determine the exact location of everything in 3 dimensions. We can then have the architectural features, the structural columns, walls, and ceilings, and then we can populate the electrical equipment, the conduits, the lighting, the mechanical equipment, hangers. Accurate data means that the new design can be started with little risk of having false existing data. We can notify the client of possible interferences, height restrictions, and it helps the client, the stakeholders of our industry, understand what's going to be built. What we use to obtain accurate as-builts is we use 3D scanning tools. We're presently using a Trimble TX5. It comes with a stand and some targets. Compatibility. We have to use, the talent is not doing the scan. The scan is the easy thing. The talent is the men and women that can wield the 6 or 7 different pieces of competing software to be able to reduce the data down to something that's usable. So first step is Trimble RealWorks, then the Autodesk Recap, the AutoCAD MEP, and then we use, because we're mechanical electrical contractors, we use Trimble 3D Pipe Designer and Trimble 3D Pipe Duct Designer, and that because it can go directly into our production software to produce what ultimately will be installed. And then we have Navisworks manage for interference and collaboration in with the other systems. So we start by using the software. This is a scan done by a TX5. And the first thing is it's stitched together using the Trimble RealWorks. And we can navigate and take measurements. You saw the slide before. It looks like an ultrasound that you would when your children were being born, the laser. The Trimble TX5 has a photographic overlay. So now we have photographic quality, but you still have the data behind it, the millions of points. And we can navigate in this particular software and take measurements. You know, did we forget to take a measurement? You go to site, will it fit down the hallway? Does it work? And we can walk through. So once we have the scan, produce the data, we never have to go back to site. All the information is here, and as the project evolves, we can make the changes. If the customer says, we have space, I'd like you to install another hot water tank, we can say, here we go. So the next step is 3D design. Using the as-built drawings, we incorporate the design. We determine if the equipment fits. Can the equipment be moved into place? Can you get from the loading dock to the mechanical room? Does it fit through the door? We can create interference drawings, penetration drawings. We can review constructability with our craftsmen, our superintendents. We can make changes with the clients for optimization. It's easy to visualize what's coming. We create accurate bills of material. We can re-estimate the project at this stage using the accurate dimensions and quantities. You need constant feedback. Is your project on track? Can you afford to do what you've drawn? We can create work packages for our craftsmen. We can break it down into bite-sized pieces that can be easily visualized and seen. We can create fabrication, assembly, and installation drawings. We create animated fly-throughs for all the project stakeholders so that they can see what ultimately is coming, they can visualize it. So here we start. The first step for us is to draw the structure. This is an actual project we have on the go, Canada West pumping station. It'll have 2 500 horsepower pumps. So the first thing we do is we draw the structure. Then we populate the mechanical and electrical systems in. Does it work? Does it fit? And then from the model, once we've created the model, it falls into our production software. We can produce drawings, fully dimensioned drawings that show all the work. This piping system is 30-inch ductile iron. It's extremely heavy. Each piece would cost about $10,000 if you make a mistake. So the extra time and effort to make sure that the process piping works pays off in dividends. And again, you can create isometrics from it, which shows how the system works, how the components come together. With the software, you can create as many cross-sections as is required to represent the job. Once you have the model, you can create infinite cross-sections. So there's no limit to the information that can be conveyed to the stakeholders. The sections are automatically updated. When we make a change in the model, the piping, all this work is automatically updated. So even your document control becomes fundamentally easier. From it, we make assembly drawings. The assembly drawings fall out our automated bill of materials. Our industry, I describe this project as using ductile iron. I was guilty of using slang. The software allows the young staff to become an expert at our industry. It's not ductile iron, it's AWA C110 ductile iron, class 53, flange by flange. Our industry has an exact language. This software allows young men and women to quite quickly become true experts at our industry, to speak our language. The automated bills of materials, which allows for the purchasing and planning. The discovery of interferences. When you make the model, it's quite easy to find your errors and start to correct them. It's easy to review the interferences and to come up with creative things. The other thing that you can do now is you can bring in the experienced individuals that have 30+ years of experience to come and give their guidance quite quickly. So with a young staff, you can produce an incredible output. And with a few experienced people, they can help correct the construction. We produce fabrication drawings that come out of the model. We create assembly drawings. So now we've made spools, and this would go to our craftsmen so that they know exactly what to assemble. Now, of course, we're going to do as much prefabrication and pre-manufacturing as possible, but again, it just shows where our industry is heading. So next, we go to purchasing. The 3D drawings are complete. We purchase our materials and equipment. We purchase the right materials, the correct amount of materials. We purchase all the interconnecting materials. If we can't draw it and work it out in the computer, how can the poor craftsman in the field be expected to efficiently and effectively put it together on time and on budget? It forces us to be complete, to be thorough, and to be accurate. We purchase in bulk, it drives your costs down, all of which reduce our cost. Next is quality control. Sorry, technical error. We purchase, this line was about purchasing the materials from the same manufacturer. The thought was, once we have a complete bill of material, you can standardize on one manufacturer for all the valving. All the pumps could be from the same manufacturer for ease of maintenance and standardization. We have better control of deliveries. Once we have the model, we can now tell everybody when we need the stuff on site. The 3D models here become the official construction drawings. So now instead of having 700 pages of spec and 300 drawings, you've reduced it down to a model that all the stakeholders can accept and work with. Ease of understanding reduces the rework, streamlines our paperwork. It fulfills our regulatory requirements. Our systems have to go to the jurisdictions having authority, and by having this all worked out and all the detail, it just allows us not to miss it. I'll show you an example a little further. Materials and equipment are installed in the correct location. So next is the productivity control. It allows us to separate the work into work packages. So if you have a 10,000-hour job, you can break it down into 10 1,000-hour packages. It's a little bit easier to keep control of. If you can't measure it, you can't control it. It allows us to allocate the manpower per work package. It allows for the extensive use of prefabrication. In our fab shops, we have specialized equipment that you would not traditionally have on a construction site, which aids in productivity and quality. Increased productivity and quality. The creation of skids, better schedule control, enhanced productivity tracking. Examples. Now here's the exciting stuff. Carleton University, design, build a boiler system. What you're seeing here is the existing steam header that's there. We've scanned it, we know what it is. The red pipe is the new steam from a new 85,000 pound per hour steam boiler. The yellow pipe in the corner, in the top right, is gas and the feed water. But there's no confusion of where we're tying in or what we're doing. This one shows the existing boiler at Carleton University. And off to the side is in our new model, is the new boiler from the shop drawings. It allows everybody to be able to visualize what the boiler is going to look like. Is there enough room for serviceability? Is this what I'm expecting? So we can all agree on what we're building ahead of time. Again, a different view. How do we run the red pipe is the main high pressure steam line, how it will be run, and you can see in the corner, you can see the existing boilers and all of that. You see the new boiler, the platform. The baby blue piping is the blow-offs. The green is the breaching off of the boiler. What we're seeing here is the front of the existing boiler trains with the animation of our new boiler with the economizer, the breaching, the combustion air. Again, in the basement, This is showing how everything is run. You can see that up in the top, the roof trusses have been simplified. We did a 3D scan, but again, the scans are so much data that we start to reduce it down. It's not important to our model, so we make a simpler representation of it. This is showing the existing natural gas. Natural gas piping is traditionally painted yellow. You can see the existing connection point and flange, and then in the brighter yellow is our proposed new pipe routing. There's no confusion about where our pipe is going to go. Does it fit? Does it work? Is it what all the stakeholders are requesting? Again, routing the piping systems through an existing facility can be a challenge. How do you represent it on a series of two-dimensional drawings? Well, then here, we make a model of it, we find a route, and we can produce as many different representations as is required so that our craftsmen know exactly what they have to do. This was an example of a project at CFB Petawawa. It's over top of 2 hockey rinks, and they wanted us to put in some air handlers, refrigeration piping, high temperature hot water, and glycol. So we scanned it, then we start to populate the model using the approved shop drawings. Then we started adding the ductwork. Now you can see that the beams on this engineered building are sloping. So because we're working with a scan with all the existing data, we can ensure that our ductwork actually fits and where it's going to end up. And again, we can populate system after system. You can see the glycol piping, the refrigerant piping, but you also get a sense of how tall or how low it is. So on this particular project, we went back to the customer and said, some of your men are going to have to be hobbits to get underneath the ductwork. Is that acceptable? So the answer came back, yes, it was, but at least we had the discussion before the ductwork was built. Here's an example of a package that ties everything together: bills of materials, codes of construction, quality assurance, quality control. So this is a refrigeration system. So the first thing we do is work out where the equipment is. We design the piping, we make bills of materials, and we make what's called a traveler, which is the paperwork that gets filled out for the regulatory requirements. So again, we make an animation of the approved shop drawings of the air handler and how we're going to do the refrigeration piping. Then we create a bill of materials, and you can see the exact material, who the manufacturer is, but you can see over in the corner is we start to populate it with the language of our industry. What is our code of construction? This is B315, which is refrigeration. What is the type of refrigeration? And how do you test it? And why? What is the pressure you're using? So we quote Bible and verse. We say in B52, table 4, the low side, the design is 166 pounds for this type of gas. The high side is 242. And we come up with what our test pressure is. Why do we test at this pressure? For how long? And because the expertise may not be there, we tell you where to find it so that we can all agree upon what we're going to build, how we're going to test it, and how we're going to document it. And you can see here the test pressure is 110% of the relief and the materials. here is what's called a traveler. So what we're asking our craftsmen now at this particular time is the refrigeration gauge, what was the model of it, the serial number, and the last recalibration date. You know, you have to do a pressure test. So we're saying we're going to do a pressure test with nitrogen, and we're going to ask for what the start pressure and time, and we're just going to document it so that we have a complete history record of how this system was put together. Now, with refrigeration systems, there's always a great debate. How do you do the evacuation? Do you pull one really good deep vacuum, or do you do what we like, a triple evac, and we define it? Instead of being subjective, we say what we're going to do and how long we're going to do it and what is a success, and document it. And in the end, it says fill out the TSSA paperwork, which is the jurisdiction having authority. So here's an example of pre-manufacturing. This is a skid drawing produced by our company, and that's what it looks like. So if you can imagine the benefit of building it all in the controlled conditions with the greatest welding procedures and processes, and then sending it to site. The reason the joints are painted white is the company is trying to determine afterwards, when they go to site, they go and see how many joints on site, welded joints, are actually not white, and then we can go back and say, if not, why not? How do we eventually become that everything that can be produced in a fab shop, in a factory, in perfect conditions, why not? This is an example of another skid, pumps, heat exchangers, the bill of materials, and there's the finished product getting ready to ship out. This is what's given to us as a design. We transform it into a 3D model, and then it goes to our production software, and those are individual pieces, and there's the finished product installed. Again, this is just drainage, but we work out all the details in advance, and then with more of the technology, once you have the penetration drawings, locating the stuff becomes quite easy. So this is what the computer is saying we're going to build. The stakeholders have all agreed to it, and here's the finished product. So that is my presentation.